Hello everyone. This video is the fourth lecture on integrated circuit layout design technology, and the main focus of this lecture is on matching. Matching is something we need to pay close attention to when designing the layout of analog integrated circuits. The performance of analog circuits largely depends on the matching of devices. Many of these mixed circuits fail to achieve the functions we expect, mainly because, well, the devices we imagine to be the same actually have different working characteristics. This, in turn, leads to issues in our circuits. That's his... Yes. So what is the main reason? Because, alas, the same devices we imagine actually have different working characteristics. This leads to our circuit performance degradation, or even failure. So let's look at device matching. What characteristics of the circuit will be affected? Let's look at the main things. For example, let's look at the bias. What about the bias circuit? This matching characteristic will affect several aspects. For example, the PVT characteristic of the bias circuit, its sensitivity. Then what is PV? It refers to process voltage temperature, that is common, voltage and temperature. So the sensitivity of these three factors depends on the degree of matching. Additionally, the operating margins, safe static control points, and safe operating ranges, among other things, are all influenced by the matching characteristics. Well, the second part, this matching, a very important impact is that for our wipe team, it will introduce an offset, that is 10. So we know that if we use a differential input, the main purpose is to suppress common mode noise, right? The premise for this is that the two differential pair transistors must be exactly the same. This way, their ability to suppress common mode noise is very effective. In practice, after processing, the characteristics of the transistors in the integrated circuit won't be exactly the same. That is to say, even if we design these two transistors to have the same characteristics, for example, both having a width to length ratio of 5.1, they won't be perfectly identical after fabrication. So, after the actual processing, it's very likely that the transistor on the right, for example, has a width to length ratio of 5.2. This means that these two transistors are inherently different. As a result, what does this lead to? An offset. So, this offset can lead to a decrease in our common mode rejection ratio, right? The decline in the common mode rejection ratio can also affect the operating range, and it might even impact our power supply. So it introduces an offset characteristic to our differential pair. The third aspect is precision, or procession precision. This mainly refers to certain converters. For example, in analog to digital converters, or digital to analog converters, these circuits heavily rely on the precise relationships of certain passive components. Fabricating capacitors or resistors doesn't allow for high precision, but accurate device ratio values are achievable. For instance, the ratio of two capacitors, C1 to C2, can be made to equal 1 with a precision of 1%. In ADCs or DACs, these ratios are used for precise analog operations. For our two capacitors, C1 and C2, we can say that we want the value of C1 to be equal to C2, and we can achieve a closeness of about 1%, or 1 part in 10,000. This is definitely possible. In ADCs or DACs, we often use the ratios of passive components, like the ratios of capacitors or resistors, to perform precise operations on analog signals. Of course, this needs to be combined with a negative feedback process. So, when we design, we expect these two capacitors to be the same, but in reality, after processing, there will be some deviations between them. These deviations can lead to a decrease in the accuracy of our ADC or DAC. This decline can further affect the linearity of the ADC, such as INL and DNL, and other factors like effective gain, all of which can be impacted by the mismatch of passive components. So for this DAC, there is a type called current steering DAC, right? Current steering DAC. So what exactly is this so-called current steering DAC? What is the so-called current DAC? Well, it means that many current sources are arranged in a certain coding way, and then switches are used to control the flow of these currents to the same resistor. In this way, different current values flowing through such a resistor will generate different voltages on the resistor, thus completing a DAC. A conversion from digital to analog. Here, the matching between currents will greatly affect the linearity of the DAC. So we say that the matching of devices will affect the accuracy of the circuit. So in this way, we can see that the matching of devices will greatly affect the accuracy of our circuit. What about the matching of devices? Well, when we are drawing the layout, we have some techniques to make the devices as consistent as possible after processing. First, we need to look at what factors can cause inconsistencies in our devices. For instance, we designed 2 transistors in the schematic to be exactly the same. So why do they end up being different after fabrication? So, we need to first look at what non-ideal factors can lead to inconsistencies in these 2 identical design devices after fabrication. The first non-ideal factor we should consider is STI, which refers to the STI stress issues. Now, this is also called LOD. What does LOD stand for? It stands for length of diffusion, abbreviated as LOD. These 2 terms actually refer to the same thing, which is the stress issue related to shallow trench isolation. Let's look at this issue in detail. Let's look at this picture. The area in the center is a MOS transistor, right? It is a MOS transistor. When we talked about the process flow before, we also mentioned that the MOS transistor must be processed in an active area, right? So the active processing happens within the active region, and outside of that region, everything is isolation, right? It's all isolation. Now, in earlier processes, this isolation was done using oxidation, right? But in today's advanced processes, we use shallow trench isolation, or STI. This means that outside the active region, we fill it with this STI material, which is an oxide. In other words, we dig a shallow trench and then fill it with this oxide material to create device isolation. Now, what kind of impact does this isolation method have on the device? Well, we say that STI is an oxide. For example, we dig a shallow trench and then fill it with an oxide material. This method is used for device isolation. So, what kind of impact does this isolation method have on the device? Well, we say that STI is an oxide. For example, typical of this, silicon dioxide, which is what we fill in the STI, right? And what about the active region? It must be silicon, right? So, the thermal expansion coefficients of silicon dioxide and silicon are definitely different, right? They are definitely different. During our processing, these different materials will exhibit different characteristics of contraction or expansion. As a result, the material of the STI will create a stress effect on the channel region, meaning it will exert a force on the channel area. This force will changing the lattice constant of the channel region, right? Once the lattice constant changes, the parameters of the device in that area will obviously change, right? This change leads to some deviations in the device's characteristics from what we expected. Now, let's take a look at an example. For example, we have a device like this. This device, the orange part represents our ridge, right? This position here is our channel region, right? And the green part represents the source and drain regions of the device, right? The device has its source and drain. Now let's take a look at how we draw the source and drain. In terms of the distance from the hook, we draw it into 4 sizes according to different degrees. For example, the longest one is that the entire area is a circular leak. In this case, we draw this circular leak to 2 microns, right? 2 micrometers. And this is case A. In case B, we make the source and drain a bit smaller, only 0.525 micrometers. And so on, the smallest is case D, where the source and drain are only 0.16 micrometers. So we have drawn 4 transistors, A, B, C, and D, right? Now note that the channel regions of these 4 transistors are completely identical, right? Their width to length ratios haven't changed at all. They all have the same aspect ratio. The only difference is the area of the source and drain. Specifically, this refers to the distance from the edge of the source and drain to the channel region. This distance changes from A to D, getting closer as we go from A to D. Now, let's take a look at these 4 transistors, A, B, C, and D, and their threshold voltages, as well as the beta parameter. The beta parameter is the beta parameter There should also be a mosquito repellent, For example, if it's an enhancement mode transistor, it's the QXWBL. Now let's take a look at the beta parameter and the pre-knowledge voltage parameter, and we can see the deviation situation. Well, the A transistor deviation is small, the dirt brightness is a small percentage of average. The pre-knowledge voltage is small. This is situation A. Then in situation B, the deviation gets larger. C is larger and D is the largest. Its beta parameter and pre-knowledge voltage parameter show a gradual deviation increase. If we enlarge the area of the original leakage region, the transistor parameter deviation will be smaller. It has this characteristic. So what's the reason? The reason is the STI. The deviation between the beta parameter and the predicted voltage parameter is a gradual change from small to large. In this case, we will find that the area of the original leakage region is larger. The deviation of the parameters of this transistor will be smaller, right? It has such a characteristic. So what is the reason? The reason is this STI stress problem, right? Why? Because we draw the original drain area larger, which means the edge of the original drain is farther from the channel area. If it is farther, because we just said that outside the active area is STI isolation, right? So these locations outside the original path are STI, right? These locations are STI. So if we make the original leakage a bit longer, what does that mean? It means that the STI is further away from our channel region, right? The further away it is, the weaker the stress's impact on the channel will be. Right, so in this way, it will reduce the impact of STI stress. So this is the impact of STI stress on device parameters, and this impact is quite significant. It can even change our cross-island characteristics by up to 20%. 20% of the cross-island characteristics. But what we need to pay attention to is that the STI stress issue can be extracted. What does extracted mean? It means we do this PX. Then do this post through PS. During simulation, the deviation caused by STI can be extracted through PX. So this characteristic can be simulated. Obtain it through post-simulation. Remember, don't leave FTI stress to the final layout check. Designers should consider the device's original leakage area early, make the STI issue part of the design, ensure it meets this condition during design, address it in the design phase, whether layout or schematic. Don't wait until the end to check. In the early stages, we should think about how large the original leakage area of the device should be, right? So it's best to make the STI issue a part of the design. It becomes part of the design. Well, when designing, let it meet this condition. So for this design, whether it is layout design or schematic design, it is best to do it in the design part and never wait until the drawing is finished. Finally, throwing it into the checking phase, that is, doing it in the later stages, will increase a lot of rework, right? So, from the very beginning, whether in schematic design or layout design, we need to consider the STI issue carefully. Situation. So let's go back and take a look at why this STI is called LOD, right? It's called the length of diffusion. From this name, we can see that it refers to the length of doping. This length of doping is an important issue, as we can observe, right? This original leakage area is actually the doped region. The different lengths of this doped region have varying impacts on the device, right? The longer it is, the smaller the device deviation will be. The shorter it is, the greater the impact of stress on the device will be. So this characteristic, this phenomenon, is also called LOD, which stands for length of diffusion. So this issue is the first one, the non-ideal problem. As we mentioned earlier, the stress in STI is influenced by the distance, right? The distance from our original leakage area to the channel. The farther its edge is from the channel. In this case, our STI will be farther away from the channel area. In this way, the stress of STI is reduced. So let's look at an example. Like this, for example, we draw a current mirror. The two tubes A and B form a mirror image of a current mirror. This area A and B is the core where the mirrored transistors are located. On both sides, we have dummy transistors. What does dummy mean? It refers to virtual transistors. A virtual transistor appears to be a transistor but lacks actual circuit function. We call it a device. Whether for transistors or non-transistor devices, we use the term dummy device. What does dummy mean? It refers to virtual transistors, right? So these transistors are virtual transistors. So What do we mean by a virtual economic transistor? A virtual economic transistor appears to be a transistor on the surface, but in reality it doesn't have any actual circuit function. So we refer to it as a device. Whether it's for transistors or for non-transistor devices, we can use the term dummy device. Now let's look at this current mirror. We add these dummy devices on both sides, and then we examine the length of the dummy devices. What kind of relationship do we see regarding the mirroring accuracy between the two current mirrors A and B at different lengths? Well, as for this relationship, we can see from this picture that the horizontal axis represents the Rice transistor. This length, right? The length of the dummy transistor is the total length of the dummy transistors. The vertical axis represents the mirroring error between transistors A and B. We can see that when there are no transistors, when there are no dummy transistors, their deviation is very large, reaching up to 10%, right? With the introduction of the dummy transistors, we found that their deviations started to gradually decrease. The reason for this is that the presence of the dummy transistors increases the size of our active layer, right? It makes the active layer larger, so that the areas outside of this virtual economic region are our STI. So when you pair it with the appearance of transistors, it causes our STI to move away from the channel regions of transistors A and B, right? Now, as the length of our virtual transistors gradually increases, so the distance between our STI and AB is the length between STI and AB. This gradually reduces the impact of STI stress on the channel regions of A and B. We can see that when it reaches 4 microns, their deviations have almost dropped to 0, right? So, a 4 micron single meter transistor is 1. It's very necessary. Having this 4 micron dummy transistor can reduce our STI stress issues to a very low level, to the point where they can be considered negligible. So this is what we have regarding the STI stress problem. All right, let's take a look at the second question, which is about a non-ideal factor called WPE, or well proximity effect. WPE, the well proximity effect. So what kind of effect is this? Let's take a look at this diagram. Let's take a look at this picture. In this picture, the central area is an N-well, which is our N-well, N-while area. So what will happen when we do this N-while? It must be done like this. Ion implantation, right? To do an N-type implantation, we must etch off the photoresist at the N-while position, right? Etch off the photoresist, and then, at the opening position, perform an ion implantation. But we need to notice that at the edge, when the photoresist is being etched, it can't just be vertical after etching, it has to have an angle. The black area represents the photoresist, and it definitely has an angle, right? An angle. So what problem does this angle cause? We can see that when we shoot these ions vertically, some ions will hit the edge of the photoresist, right? They will hit that edge. So what will happen to this edge? It will form something. This is the reflection, right? The reflection will be reflected to the edge positions of the N-well. So what will this cause? That is, it will cause the edge positions of the N-while to have a higher concentration. The concentration will be higher than the central area of NYL. So the landscape deviation effect will lead to a higher concentration of N injection at the edge of the processed N-well. In other words, the substrate concentration in the N-type region is higher. The substrate concentration in the surrounding area is higher, right? So what will happen if the substrate concentration in the surrounding area is high? That is, if we are in this area. If we place some PMOS transistors around the edges of the N-well, because the concentration in this part of the N-well is high, it will cause the threshold voltage of these PMOS transistors to be higher, right? It will make the threshold voltage in this area higher. Of course, I'm talking about the absolute value of the threshold voltage. The absolute value of the threshold voltage will be higher. So let's take a look at this. The result is like this. In the diagram on the right, what does the horizontal axis represent? It represents the size of the N-well, meaning the distance of our transistor from the edge of the N-well. And then the vertical axis represents the current deviation of the current mirror, which is the deviation we get from the electrical mirror. We can see that this deviation is all negative, meaning that the current we get from this mirror is lower, right? It's lower. The reason it's lower is that the threshold voltage of these surrounding PMOS transistors is higher, right? So if the threshold voltage is higher, then the current from the mirror will definitely be lower, right? So we can see that the current mirrors near the edges of the N well have a very high deviation. And then, as we move away from the edge of the N well, we can see that the deviation gradually decreases. And when we reach about 14 micrometers, it's almost gone. Right? It's almost gone, or at this point, it's actually acceptable. It's definitely lower, right? So we can see that the current mirrors near the edges of the N well have a very high deviation. And then, as we move away from the edge of the N well, we can see that the deviation is gradually decreasing. By the time we reach about 14 micrometers, it's almost gone, right? It's almost gone, or at this point, it's actually acceptable, right? At 4 micrometers, the deviation has already reached 0.05%. This is actually very small already. So this diagram illustrates that our PMOS transistors, the further it is from the edge of the N well, the smaller the degree of deviation will be. So this is the geometric effect. The geometric effect. Overall, well, this is it. Transistors near the edge of the well will have different, what should I say, threshold voltages. If the threshold voltages are different, it will lead to different operating currents. Then these tubes have different characteristics from those of our transistors, far away from the edge of the well. So this will also cause deviations in our devices, right? For example, we designed these two transistors A and B exactly the same, but we didn't notice the scenery effect when we drew the board header. For example, both AB transistors are PMOS tubes, and the APMOS tube is close to the edge of the N well. So what about the BP cap transistor? It is closer to the center of the well. So what happens? After processing, it will result in the absolute value of the threshold of A. So the threshold voltage of A will be a bit higher than that of B, right? In this case, the two devices will be mismatched. So this is the geometric effect. The third one is the polyproximity effect, abbreviated as PPE. This refers to the effects of polysilicon proximity, the polyproximity effect. So if we understand it literally, it actually means that when it is close to polysilicon, it will also have some deviations, right? Let's take a look at what this phenomenon is. In fact, when we are processing this gate, we need to etch the polysilicon, right? We want to keep the polysilicon in the channel region and remove the polysilicon outside the channel region. During the etching process, there is an issue with etching speed, right? What affects the etching speed? It is actually influenced by the density of the polysilicon. For example, take a look at this diagram. We can see that we have drawn 6 gates, right? Let's assume these 6 gates represent our 6 fingers. We are making this transistor with 6 fingers, right? Originally, when we designed it, all 6 fingers were identical. When we laid out the design, these 6 polysilicon areas were also exactly the same, right? But then we can see that, for example, we have drawn gates 1, 2, 3, 4, 5, and 6, right? We have 6 gates, and let's assume these 6 gates represent our 6 fingers. So we designed this transistor with 6 fingers, right? Originally, when we designed it, the 6 fingers were completely identical. When we laid out the design, these 6 polysilicon areas were also exactly the same, right? But then, after processing, there will be deviations. What is the reason? Let's take a look. For example, next to the gate on the far left, there is a very large area of poly. For example, this is another transistor. It is very large and close to the leftmost finger, right? And there is no other poly on the right side of the rightmost finger. What phenomenon will it cause? What will we find in class? The far left finger has a large area of gate around it, so its etching speed will be relatively slow. So after processing this finger, L is its length, right? Its length is longer, right? Because the class is slower, so it is longer. Then look at the 1234 in the middle. These 4 fingers. Hey, these 4 fingers are more consistent. Why is that? Because you can see that the surrounding environment is quite similar, right? The environments around these 4 fingers are similar, so their etching speeds are relatively consistent. Therefore, after processing, these 4 will be more uniform. Now, what about the one on the far right? The length of the one on the far right will become shorter. The reason is that there is no polysilicon on its right side, so its etching will be faster, which will lead to its length. becoming shorter. So you can see that it's because the environment around the polysilicon is different, which leads to variations in its etching speed, and consequently, this causes some deviations in its dimensions. So, this is the polyproximity effect. Now, what does this proximity effect lead to? It means that the polysilicon near our transistors can cause some stress issues, which can affect the consistency of our etching process, and also impact the characteristics of photolithography. So, this is the problem of polysilicon proximity. Now let's take a look at the fourth one, which is the non-ideal characteristics. This is called the metal over transistor. The metal over transistor means that we have metal covering the transistor. Covering the metal, this will also cause some of this. So why does this happen? This brings us to a process called annealing, right? Annealing is a crucial step. The content, right? Generally speaking, after processing integrated circuits, we need to complete the annealing step. What will happen during this annealing step? It will remove some oxygen atoms in the silicon, and it can also allow our doping, that is, doping and our normal silicon, to form such a perfect lattice structure. Annealing is required. So what happens during the last annealing step? We often need to inject hydrogen. The reason for injecting hydrogen is that, as we mentioned earlier, it helps to remove some oxygen atoms from the silicon. So, this hydrogen injection will be affected by the metal barrier, right? If we cover the entire surface of the chip with metal, then when we try to inject hydrogen for cleaning, it definitely won't be able to penetrate, which can lead to some issues. For example, let's look at this case, where we have two transistors, A and B. So on top of transistor A, right? We covered it with some metal, right? We covered the entire thing with metal, a higher layer of metal, right? And then transistor B wasn't completely covered. So when we perform the hydrogen injection for cleaning, we find that in the area of transistor B, the hydrogen can flow in smoothly, right? But for transistor A, that's not the case. It's blocked by the metal. So in this case, during this entire cleaning and annealing process, what will the presence of this metal affect? It will also hinder the annealing process. Furthermore, it will introduce stress problems. What will it introduce? Defect problems, which will cause some deviations in the two devices A and B. So this is a problem of metal over transistor. Of course, generally speaking, it is not recommended in design rules. It is not recommended. Using metal to cover the transistors usually means that there are requirements for the area above the transistors, especially above the gate. That is not allowed. High-rise metal covering is usually recommended, but it is not absolute. Sometimes, because the area of your layout is very limited, then in this case, sometimes it will happen. When it comes to covering the devices with metal above the transistors, we need to pay special attention to the issues related to the metal over transistor during the hydrogen annealing process. Then let's look at the fifth question. The fifth question is called asymmetry, which means non-symmetry. The four problems we talked about earlier are all about AB2 transistors, right? They are all AB, that is, we have two transistors A and B, and then because of the two transistors A and B, for example, the area of the circular leakage, but the position of the well, the condition of the metal above it, and so on. The difference causes A and B to be different, right? Then let me look at the fifth question. Actually, the fifth question is that a single an A transistor will be different. Why is a transistor different? What is the main reason? When we draw a transistor, it will have an original drain area, right? So from our layout, there is no difference in the original drain area, right? You can think of the circle as a leak, or you can think of the leak as a circle. In the diagram, there is no difference between the circle and the leak, but in reality, the circle leak after processing is asymmetrical, and the circle and the leak are different. They can't be interchanged. So what do we call this? We call it asymmetry. Now let's take a look at why this asymmetry occurs. This brings us to the ion implantation process. We can take a look at the 110 crystal plane. This is the arrangement of silicon atoms on that plane. We can see that on the 110 crystal plane, there are many channels. These positions have their atoms arranged. The density is very low. It creates gaps at these positions, forming voids. So if our ion implantation is done perpendicular to this 110 crystal plane, what issues arise? It leads to what we call the channeling issue. The channeling issue is when we implant these ions, they will penetrate very deeply along these gaps. The density is extremely low, right? As you know, it will form a significant gap. So if our ion implantation is potentially perpendicular to the 1100 crystal plane, what problems will arise? There will be the so-called channeling problem. The channel problem is the tunneling phenomenon. The tunneling phenomenon means that when we inject these ions, they will be injected very deeply along these gaps. Because there are no silicon atoms in those positions to obstruct the ions, right? So the implantation goes very deep. This is actually something we don't want to see. Ideally, we want the ions to be implanted at a shallow depth with a certain concentration, rather than driving the atoms very deep. So what can we do about it? So typically the implantation will have an angle called tilt, right? There will be an angle, usually about 7 degrees. That is, we tilt our 110 crystal plane by 7 degrees, right? Tilted by 7 degrees. Or the direction of our ion implantation is tilted at 7 degrees. In short, the direction of the ion implantation should form an angle of 7 degrees with our 110 mirror. So, if we twist the 110 crystal plane by 7 degrees, then when we inject ions perpendicular to the screen, we find that it is... The density of atoms is relatively high, right? Relatively high means that this will not happen. So, in situations like the gaps on the left side, the implantation will be affected by the presence of some atoms acting as barriers, which means it won't penetrate very deeply. Instead, it will form a shallow layer of implantation. So, why does this tilted implantation lead to deviations in the source and drain? The main reason is that we can see this by looking at its cross-section. The one on the left is a transistor, right? It's a transistor. Now, when we form its source and drain, if we perform a tilted implantation, say at a 7-degree angle, after tilting, we can see that because there is a gate, right? The gate is 3-dimensional. It protrudes out a bit. So, what happens then? It will create a shadow in that area, right? It will form a shadow, which we call a shadow. Imagine a wall with light shining on it, creating a shadow where light can't reach. Similarly, the ion column's gate creates a shadow, blocking ion implantation in that area. This causes different overlap regions with the gate. On the right, the area receives ion implantation, resulting in a larger overlap. The shadow, right? The position that can't receive light, right? So it's the same for this ion column. Because of the presence of the gate, it creates a shadow for ion implantation at this position, meaning that the ion implantation can't reach this area, right? As a result, we see a phenomenon where the overlap of the two implantation regions with the gate is different. On the right side, because the entire area can receive ion implantation, the overlapping region will be larger. More. So here, for example, the extension of the bottom of the gate is more, and on the left, because the edge of the gate is a shadow position, it cannot receive the input, right? So in this case, the overlap will be very small, relatively small. Well, someone may ask, why is there overlap if there is no ion implantation here? What needs to be noted here is that after the ions are implanted, they will diffuse, right? So even after implantation here, if they slowly diffuse, they will also diffuse to this. Under the gate, right? The distance of diffusion is quite limited, right? So the degree of overlap will definitely be smaller than that. On the right side. So, as we can see, after the entire processing, the two implantation regions are indeed different. For example, if I treat this area as a circle, this is low, then the overlap of this circle with the ridge is different. The parasitic capacitance, right? The overlap of the parasitic capacitance with the circle and the ridge is different. So this leads to the source and drain of the device being different, right? The source and drain themselves are not the same. They're not the same, not the same. All right, let's take a look at the sixth question about gradients. So, what is this problem? This is mainly due to some processes or thermal gradients, which have some impact on our circuit. So the thermal aspect is pretty easy to understand, right? It means that the temperature of the chip is different at various positions. If there's a thermal gradient present, it will cause the characteristics of the devices at different temperature locations to change in different ways, right? And also some process deviations can lead to gradients as well. For example, the concentration of residues or the thickness of the oxide layer. These can also vary at different positions. There is a different change, right? Then there are some deviations in the process, which will also cause some gradients such as this. The concentration of the residue, or the thickness of the oxidation, will appear in different locations. This linear gradient change leads to some deviations in the devices at different positions. Let's take an example like this chip. For example, take this chip. Let's say its oxide thickness, TOX, is thinner around the edges compared to the center. So there will be a gradient change, right? The gradient change we can see is position A. The thickness is different from the thickness at position B. So if we draw this at position A, if we place a device at position B as well, then these two devices will have different oxide layer thicknesses, which will lead to what? This will cause their threshold voltages to change differently, right? For A, the oxide is thicker, so the threshold of A will be higher, which is a high threshold, right? For B, the threshold will be relatively lower. So in this case, their VTH will deviate. So this is the influence of gradient. Let's take a look at the seventh topic, which is also known as side etching. Sometimes it's referred to as undercut action. So what is this phenomenon? Let's find out. Actually, when we are in this class, it will actually extend to the two sides of the figure. The edge will extend apart. For example, when we are processing a gate, when we draw the schematic diagram before, it is like this, saying that this is a substrate, right? There is a gate on it. When we draw this gate, the edges of the gate are supposed to be perpendicular to the silicon surface, right? But that's in an ideal situation. In an ideal case, it looks like this, right? When we etch, we remove everything outside of this edge, right? We only keep the edge. But what does the actual situation look like? In reality, during the etching process, because etching relies on chemical agents, right? Even though there is an anisotropic etching condition, it will still cause some etching on both sides, right? So let's take a look at this. For example, there is a photoresist protection on the poly layer. Then the poly layer in other places without photoresist protection is all knocked off, right? It is all knocked off, but the edge part will be knocked off, right? The edge of the photoresist will be recessed. What will this form? It will form the poly, or our gate. Our gate will have a recessed part here, right? So what do we call this? It's quite vividly called side etching, right? Because both sides will also recess inward a bit. Once these two sides recess inward, what will that lead to? It will lead to a situation where the dimensions become relatively smaller, right? They will become smaller. So the size has relatively become smaller, right? It will be a bit smaller. In other words, we were supposed to etch up to this point and stop, right? Etch up to this point and stop. But in reality, it ended up etching a bit more. So effectively, it might have become this wide, right? So it ends up being this wide. This will cause our dimensions to have what we call a fixed deviation. So there is a fixed shrink. There is a fixed shrink like this. So let's take a look at an example. For instance, let's draw a rectangle. Rectangle. The rectangle on the left is a long strip. For this rectangle, we only care about its height. If I draw X, and then I draw two more rectangles, the height of these two rectangles is Y. Then X to Y is exactly equal to 2, right? X to Y is exactly equal to 2. So we draw it like this. So when I draw, I hope that X is twice Y, right? But what happens after processing? Because of the existence of this set action, the pattern will shrink inside, right? And the degree of shrinkage is fixed. It's fixed. So let's take a look. After the shrinkage, this x, it actually will shrink to the position of the implementation box, right? The height y will also shrink to the position of the implementation box. And the distance of this shrinkage is the same, right? This shrinking distance. The distance of shrinkage is fixed. It's fixed. So after the shrinkage, that is to say, after our class, after processing, what does the actual pattern we obtain look like? The actual pattern we obtain is, it's x1 prime. And then the outside of this side actually becomes an outer stroke, right? An outer stroke. Then it is very obvious here that is the x stroke is not equal to the y stroke, right? It is not equal to 2, because if you shrink, it is a fixed shrinkage. It won't change just because you say y is half of x, so the degree of shrinkage doesn't become half either. It's not a proportional shrinkage, it's a fixed shrinkage. So this will definitely lead to the final result, where x prime compared to y prime is no longer equal to 2, right? This is the phenomenon of side etching. So this phenomenon will also lead to adaptation, right? It will also lead to adaptation, which is what we originally expected. The x7 key and the y7 key have a 2-to-1 relationship, but after actual processing, it no longer satisfies the 2-to-1 ratio, right? Deviations occur. So what is this last non-ideal characteristic called? It's called random mismatch. Random mismatch refers to random adaptation. Random adaptation. So what is this random mismatch phenomenon? Let's take a look at it in practice. We believe that nominally identical devices are actually affected by what? They are influenced by a limited degree of adaptation. This adaptation is due to some uncertainties in each step of the processing. Each step has some uncertainties which can cause mismatches in our devices. For example, let's take a gate like in a MOSFET, right? We have this MOSFET and we draw a layout like this. Now, when we draw this gate, it's very flat, right? But what happens after actual processing? In reality, there will be a lot of what we call microscopic variations, which are tiny microscopic changes. In other words, if we zoom in on the edge of this gate, it actually isn't smooth, right? It's chaotic and changes in a disorganized way. So these things, are due to the uncertainties in each step of the processing. These tiny variations can lead to some mismatches in our devices. Right? So we drew two transistors. We drew two transistors. Even though these two transistors are drawn the same, if we zoom in to look at the edges of the gates, they're actually not uniform. The processing condition of the edges is actually irregular, right? So these irregularities are a random phenomenon. It's a random phenomenon. And it definitely isn't deterministic, right? It's a random phenomenon. Since it's a random phenomenon, it means that the fluctuations in different transistors will definitely be different. Consequently, this will lead to deviations between the two transistors. Right. So let's take a look. Actually speaking, we want to process a shape. For example, we want to process a square with a side length of x. Then we draw x, but after processing, its side length must have a delta x. What? Deviation. And delta x is random, right? So we use the standard deviation of delta x to measure the extent of this deviation. We use its standard deviation, represented by sigma, to express this. The situation of adaptation. All right. So in the previous part, we introduced the 8 basic situations that can lead to device adaptation issues. Now, the next part is very important. How do we respond to these 8 situations? In other words, what methods can we use when drawing layouts to address the adaptation problems caused by these 8 situations, right? All right, let's take a look at the first method we can use to respond, and that is the DAMI flagship. In fact, we already mentioned this when discussing STI isolation, right? So, what is it? It's called a virtual flagship. In other words, it doesn't work. That is to say, According to my schematic diagram, it doesn't work. But it will appear on the layout. Its presence is mainly to address some of the issues we just mentioned. So, what are the main issues? Let's take a look. LOD stands for length of diffusion, right? WPE stands for well proximity effect. And then, these include STI stress issues, layout bias issues, and polysilicon proximity effects, right? All of these can be addressed using this device. So, how exactly do we solve these problems? We can understand this better by looking at an example. That's it. The STI stress issues, layout bias issues, and polysilicon proximity effects, right? All of these can be addressed using this device. So how exactly do we solve these problems? We can understand this better by looking at an example. Let's look at an example. So what example is it? This is its schematic, where we currently have two pairs of transistors, and the first and second, this part. So these are the first and second transistors. Of course, the first and second refer to the drain connections. Now, these two pairs of transistors need to be matched, right? So, for this part, we need to perform a matching operation between these two transistors and those two transistors. How do we do that? We need to consider adding rice, right? That means we should add rice transistors near these two transistors. We also add rice transistors on this side. So how do we do this on the layout? Let's take a look at how it's done. This part is G1, these two transistors. G1 are actually two fingers that are combined together in parallel to form one transistor. Then, this is D1, which is its drain. And this is the gate of the second transistor, while this is the drain of the second transistor. So the source of these two transistors is connected together, right? So, here. What is this area? It's the core area of these two transistors, the actual region of these two real transistors. To protect these two transistors, we need to add some rice on both sides of them. So let's take a look. On both sides, we've added one, right? This is the debit, and over here, we also need to add the debit. After adding a large area, let's take a look at its cross-section. The cross-section looks like this. Let's look at this area. It is the core area of our two tubes, right? The core area. So if we want the two tubes to be more consistent, we actually have to protect the core area. So how to do it? Let's take a look at the stress problem of STI. Well, on both sides of the core area, we put rice transistors, right? So you can see that the STI is running here, right? This is the STI. If you don't have rice transistors, this position, well, this STI will extend here, right? If the STI were to extend out, it would directly affect the G1 below, right? But now the FTI has come here, because we've placed two rice transistors, right? If I added more, the STI would be even further away. So we can see that in this case, STI has an impact on this core area. So, the stress in this core area has been reduced, right? It's been lowered. This way, what does it achieve? It weakens the LOD issue. At the same time, we can see what type of transistor this is. This is a PMOS, right? It's a P-type, so it's processed in an N-well. The yellow area represents the entire N-well. Now we can see that because of the presence of this transistor, it also causes the transistor in the core area to move away from the edge of the well, right? The edge of the well is over here. The edge of the well is here, so this edge is further away from our core area, right? In that case, the proximity issue is also resolved, right? The proximity issue is resolved. Now, let's take a look at the polysilicon proximity issue in the core area. We can see these four gates, 2G1 and 2G2. You can see that because of this. Its presence ensures that the environment on both sides of the gate in our core area is completely the same, right? Look at this gate. It has two identical gates on both sides. So this is the same, and this is also the same, right? Each gate in the core area has identical gates on both its left and right sides. So in that case, because of this, polysilicon proximity issues. The problem that caused the gate to be different has been solved, right? You can see this. What about the left side? Because there is no gate on the left side of the gate without git, its class speed will be faster. So the gate will become narrower, right? This will also become narrower, but the other parts will not change. Pay attention here. In my diagram, when I say this thing is recessed, it refers to the polysilicon critical effect, which affects the etching speed. It's not caused by the side etching, right? The side etching exists for all these gates, and of course they all have the same side etching issues. The side etching is the same for all of them, including this one, which also has side etching, right? The side etching is the same for all of them. So because of this, what does its presence mainly solve? The polysilicon proximity issue. So the polysilicon proximity issue affects the gate of the larger structure, right? It doesn't impact the gates in our core area, right? So with these methods, we have directly resolved it. The adaptation issue between these two tubes, G1 and G2, is caused by the LODPEP phenomenon, right? These adaptation issues have been resolved. Now let's take a look at the second issue, which is how to solve the metal over transition problem. Actually, there's a very straightforward solution, which is called no metal, right? It's pretty obvious. We just don't put any metal on top of the transistor, and that solves the problem, right? So that issue is resolved. However, there's another method we can consider. Let's take a look at it. First of all, let's talk about the thing on the far left. Yes, there is an A. For example, this is transistor A, and this is transistor B. If we draw metal on transistor A, but not on transistor B, then this is obviously not possible, right? Obviously, transistor A will be blocked by the metal, which will affect the hydrogen annealing problem, but transistor B will not be affected, so transistors AB are different. So this situation is very undesirable, very undesirable. Then let's look at the middle situation. In this middle situation, the two transistors AB are covered with metal. Did you see that? I've covered both with metal, so in this case both A and B will be affected by this clear barrier, which will influence the injection of hydrogen and the hydrogen annealing phenomenon. So both devices A and B will be impacted. The conditions are the same, right? The impact is the same. So, theoretically, A and B will be more consistent with each other, which means the matching degree will be better. However, this situation also requires a lot of caution, right? It's very small, because even though A and B are the same, both A and B will be affected, meaning the impact of this hydrogen annealing process means that both A and B will show some deviations in their characteristics. Although the degree of deviation is the same, the characteristics of both A and B will deteriorate. So about this, you need to be very careful, very careful. This means that this method should only be used in situations where space is extremely tight, right? So what is the most recommended option? The most recommended one is actually the third option. This is the most recommended one, and this is the third option. So what is it? It's called no metal, right? For both A and B, we don't draw any metal. On top, there's no metal here. In this way, both A and B won't block the hydrogen annealing process, or the hydrogen injection during annealing. This means that the characteristics of A and B are quite good, and also more consistent. So this is the best recommendation on how to solve the metal over transistor issue. So let's look at the next one, which is how to solve the assignment problem, which is asymmetry, right? Asymmetry means that when it comes to the original leakage area, it is different in itself. How to solve this, problem? We should pay attention to what we use when using the mirror method. First of all, what should we say? First of all, the placement of our period must be very particular. That is to say, the current direction of two devices to be matched must be consistent. For example, if we have two transistors A and B, the current flow direction of A1 and B must be consistent so that A1 and B can match. Otherwise, it is difficult to match, for example, the one above. For A, the current flows from left to right, and for B from top to bottom. In other words, the placement of their gits is inconsistent. The gits are perpendicular to each other. In this case, it is difficult to match A and B, right? It is difficult to match. The simplest way is that due to the tilted injection problem, A and E will be different, right? For example, if I tilt in this direction, what can I see? A. It will be affected by the shadow problem, right? It will be affected by the shadow but B will not be affected, right? For B, because your injection direction is parallel to my original direction, it can be recorded and there is no shallow problem. So this will cause A and B to deviate, right? So what should we do? We must make sure that the gates of A and B1 are placed in parallel and consistent directions. For example, if A is configured as W6156, then B should also be oriented from the left as W6. This way, the direction of current flow will be the same, allowing for better matching. Now let's take a look at how we can make the original leakage of a single transistor more consistent. Here, we can mainly use techniques like finger and multiplayer to address this. First, let's talk about fingers. To make the original leakage more consistent. Here, the main thing is to use finger and multiplayer to solve the problem. First of all, the first one is finger. So I take this transistor, this long and large transistor, and break it down into several fingers. For example, I've split it into 4 fingers. So finger equals 4F, which is 4. Then, to differentiate the original leakage areas, we use different colors, right? For example, we use gray for the original leakage, green for another type, and red for the gate. Let's guess that finger is equal to 4. Let's draw it like this. So we draw the original leakage areas together like this, and of course the leakage must be connected, right? This is how we draw the fingers. Now let's take a look at the cross-section. It looks like this, right? The cross-section diagram is turned like this, and then, for example, our injection is in this direction, and it is injected like this, right? It is injected like this. So, if we do it this way, all the gates on the left side will have this shallow issue, right? They will all have the shallow problem. You can see that the overlap on the left side of the gate will be smaller, right? Now, regarding the leakage of this gate, the overlap on the left side will also be smaller. Similarly, if we look at the overall area, we can see how the overlaps are arranged. Now, if we look at the area, we can see how many long focal points and how many short focal points there are, right? We can observe the small overlaps and the large overlaps. This overlap is relatively small, while this overlap area is larger, this one is smaller, and this one is larger, right? So you can see that for the circle, there are 2 small overlapping areas, plus 2 large overlapping areas, which makes the circular region look like this, right? Now for the leakage, you can see that this overlap is large, and this overlap is small, right? This overlap is large, and this overlap is small. So in this case, you can see that the leakage also consists of 2 small intersection points, plus 2 large intersection points. So after doing this, we can see that the total overlapping area of the original leakage is equal, right? When we look at the circle and the leakage together, they are equal. So in this way, we have addressed the original leakage. Because of this, the overlap of this gate is different. So by drawing it this way, we can make the focal points more consistent. This issue can be resolved through the use of fingers. Well, there are actually some issues with this. What I mean is, our original path area has something else, right? The parasitic effects of the PN junction, right? So, because we are breaking this down, since we have 4 Gs, the number of original paths that come out will be different. So, the parasitic effects of the PNG will also show some discrepancies, deviation. So because of this problem, there will still be some inconsistencies in the original path. So what is a better way? Use this, right? We use this, for example, our m is equal to 2, multiple. Then what do we use? Use the mirror method. The mirror method. After m is equal to 2, we make a central axis, and then make a left-right mirror image. After the mirror image, the left side of the tube is a circle, and the right side is a leak. The left side of the tube is a leak, and the right side is a circle. Then, if we look at the cross-section again, what will we find? The number of circular paths is the same, right? Then, the intersection is also the same. The circle is one big one, one small one, and one big one. If there is a leak, it is also a small one and a big one. So through this, we can get this. If we make the original drain of the transistor more consistent, we can solve the problem of tilted injection. All right, let's look at the next topic, which is about gradients, right? So, how do we solve this gradient issue? Here, we actually need to break it down into two situations. The first one is one-dimensional gradients, which means there is a gradient direction in one dimension. The distribution of gradients. So how do we solve this? We use what is called common access, called the common axis, using the common axis. Use the coaxial method to suppress the gradient change of this single dimension. So how do we specifically solve this? Let's take a look at this example. For instance, we have a diagram like this, right? In the x direction, there is a gradient, like the thickness of the oxide layer. So if I put a transistor A at this position, and a transistor B at this position, then obviously the thickness of A should be higher than that of B, right? So the threshold of A should be higher than that of B, which will lead to a very obvious deviation between A and B. In order to suppress this problem, how can I use the coaxial center? I can do this. I want to put A and B, break them down into two smaller tubes in parallel. You see, I need to change both A and B to M equal to 2, which means the multiplier is 2, and it will be oriented like this. So for A, we have A1 and A2, and for B, we have B1 and B2. A1 and A2 are in parallel, and B1 and B2 are also in parallel, right? And then their placement positions have some variations. For A, A1 is placed here, and A2 is placed there, while B1 and B2 are both placed in the middle, right? After doing this, we find that, hey, for the A tube, A1's threshold is very low, right? It's very low. The threshold of A1 is very low, right? It's very low. And then the threshold of A2 is very high. So after connecting the two in parallel, a medium threshold will be formed, right? It creates an intermediate threshold. Then, if we look at B1 and B2, we'll find that B1 and B2 are positioned right in the middle, which gives us an intermediate threshold, right? So after drawing like this, their axes actually coincide, in this case, from the x direction. Changes in this parameter, the combined effect is the same, right? So this will make A and B even more consistent, right? More consistent. So how do we commonly draw the coaxial method? It can be done like this, right? For example, in situation A, we have two tubes, A and B. B is placed here, and A is placed on both sides, right? That's one way. Another way could be that I don't split B. I place B in the middle and put A on both sides of B, right? This also means that the axes of A and B overlap, right? You can see this is their axis. Now, looking at the situation with B, right? In the case of B, we replace the transistor with ABAB, right? The axes of A and B are at these positions and they don't overlap, right? But it's important to note that their axes are getting closer together, right? The axes are getting closer together, and as they get closer, here, the axes of A and B are both located here, right? Now, let's take a look at the situation with B. In the case of B, it replaces the transistor with ABAB, right? The axes of A and B are at these positions and they don't overlap, right? But it's important to note that, what about its axis? It's getting closer, right? The axis is getting closer. So what if it's getting closer? So how about that? The deviation will also decrease, right? So even though they don't completely overlap, it will still help to suppress some of the deviation. This is what we call controlling the axis. So when we talk about coaxis, what it really means is that we need to transform the transistor into a sort of interleaved structure where A and B alternate like this. Well, then what does that make? Two identical transistors have the same what? The same axis, the same axis. How do we do that? Generally speaking, we need to divide the transistor into several equal parts, especially the sub-finger. For example, in this example, we divide it into 4 fingers. And then what? Then draw them in a paper insertion shape. For example, AB2 devices, AB2 devices. What is this? AB is an insertion team. This is an insertion team of a PCAP tube. Then their circles are connected with one node, and the leak, they are 2 or 3 nodes respectively. These are 2 bullet screens, right? Now we need to draw A and B with a coaxial center, that is to disassemble A and B. What about A? M equals 4. For B, let's make M equal to 4. Then I arrange A and B in this way, ABAB or ABABA. Then what is their axis? Yes. It means that they are closer or reaching a state of overlap. So, this has achieved a state of overlap, right? The axes of A and B are both here, right? The axes of A and B are both here, which is a state of overlap. Now, for this arrangement, the axes of A and B don't completely overlap, but they are much closer together, so it can still help suppress the effects of one-dimensional gradients. Now, after breaking it down like this, let's take a look at how to draw the layout. For example, on the left, we have ABBB, and this is how we draw it. Here it is, ABBB, and then connect the corresponding circles and loads according to such a schematic diagram. And the one on the right is ABABA, it's the same. This is an example, a case study. We will discuss suppressing the two-dimensional gradient, meaning changes in gradients across 2 dimensions. We need to use a cofinger. This control center is crucial for layout drawing and interleaving. Thus, when we talk about two-dimensional gradients, there are gradient changes in both the x and y directions. Here, using a coaxis is ineffective. This is the control center. This is a very important layout drawing technique, a new method for interleaving. So, when we talk about two-dimensional gradients, it means there are gradient changes in both the x and y directions. At this point, using a coaxis is not very effective in solving the problem. It's not very easy to solve. So at this time, we need to use the common center. For example, this energy, this one here. It's xy, like x and y. In both directions, there is a linear gradient of parameters. So if we draw a transistor A at this position and a transistor B at that position, and we want them to match better, we actually need to split A and B as well. After splitting, the arrangement looks like this. A is split into 2, and B is also split into 2. Then A is arranged in a diagonal manner. We arrange them in a diagonal manner like this. This is A1 and this is A2. For B, we have B1 and B2. This is how we arrange them. After arranging them this way, we can see that the centroids of A and B are actually right here. Right? They're both here, so this way, the parameters of our combined devices, A and B, will all fall onto this point, just like they land on this point. This will make the two devices, A and B, even more consistent. For example, let's take this case where we want to draw a differential pair. At this point, we have an NMOS, right? This is an NMOS differential segment. So, a differential pair pops up, and this is the input side. We need to connect them together at the input side, while the output side is separate. We have 2 gates, which are M1 and M2. Now in this case, we need to draw the layout, and for that, we will split M1 and M2. Right. When we split it, what do we get? M equals 2. So in this way, we place the 2 M1 transistors here. And this means their aspect ratio has become half of the original, right? This is 1, 2, M1, and this is another 1, 2, M1. We arrange it this way. And M2 is placed diagonally. This is 1 to 2 M1 and this is 1 to 2 M2. After arranging it like this, we can see that if there is a certain kind of two-dimensional gradient, it creates a gradient change. So, because we arranged them diagonally, we can see that for each small transistor, like this is the source, this is the drain, and this is the gate, we can observe that the centroids of the source, drain, and gate actually all fall onto this node. Right? They all converge at one node, which means that the combined device parameters of M1 and M2 are equal to this node. So this makes M1 and M2, they're more consistent now, right? More consistent. So it can also be done like this. We can overlap them. For example, these 2 pipes, if I treat the middle position as a primary stage, then in fact, I can overlap them together, right? It's the same. So what about this? The first order gradient, that's what's linear, right? Linear xy. Gradients in both directions can be eliminated, but it should be noted that such a connection has a price. What is the price? The interconnection between metal and poly will be more complicated. Right? This must be the case because originally M1 is a tube, M2 is a tube, and then M1 and M2 are 2 tubes. The whole thing is placed on both sides and then simply connect them, right? But now this M1 is split into 2, and it is still placed diagonally like this, right? Then I first need to connect this 1, 2, M1 with this 1, 2, M1 in parallel, and then connect these 2 M2s in parallel to complete the connection of this schematic diagram, right? It's obvious that this connection is going to become much more complex So this means that when we do co-centering drawing, one of the costs is that the connection becomes more complicated. So what negative effects will the complex connection bring? As we said before, this connection, metal wire, or throw-off, right? It will definitely have parasitic resistance and capacitance, so such a complex connection will cause the fuselage to deteriorate. The parasitism becomes worse. So this means that the drawing of a layout for paper towels will bring about a parasitic effect. Now let's take a look at common layouts for paper supply systems, right? The simplest one is called cross, coupling, which is this square cross layout. In this layout, two components are each split into two parts and arranged diagonally. So the top, left, and bottom right are A, while the top, right and bottom left are B. This arrangement completes a common centroid. Then we can also decompose A and B more. If we decompose more, what will happen? We can suppress higher order gradient distributions. As we mentioned earlier, this simple square cross layout can suppress a first order gradient, right? But if this gradient is not linear and is of a higher order, then we need to decompose the components even more. This way, we can suppress the changes in higher order gradients. So if we decompose them even more, we can arrange them like this, right? This is AB, and then we have ABA, and then BRB. So on the left, we have a square cross layout of ABA, and on the right, we can do it again, creating a mirrored version. Right, in this way. So the centroids of A and B will both fall on this node, right? They will land here, which makes it more consistent, right? More consistent. All right, this table shows some frequently used decomposition layouts for common centroid matching. Most of the time, it's about matching two components, such as A and B. So how do we put it? The simplest way is ABABAB, which is a relatively small decomposition. If we want to suppress the higher order, we have to decompose it more, right? We even have to decompose it like this. If we decompose it like this, it must be said. Suppressing higher order gradient changes. But it's obvious that everyone's concern is that the wiring has definitely become much more complex, bringing a lot of parasitic issues. Here we have two components, and we can also do this with three components. This is an example with three components. If we want to match the three flagship models of ABC, we can also use this kind of controlled drawing. Alright, so this is an example of a paper supply system. Now, what is this example using? ABABA, and below is the placement method of BABAB. Using this arrangement, we can create a common reference heart layout. This is the reference heart, and let's see how it's done. Now, looking at these two devices, AB for example, this is an N tube, an NMOS split input tube, and its original end is definitely connected together. The drain end actually has two outputs, and there are also positive and negative inputs, right? So, when these two tubes are used to create a common axis, AB is definitely divided into several parts, right? According to this, A is divided into 8 parts, and B is also divided into 8 parts, right? For example, in this case. It's the same as the way it's arranged. The top is ABABA, and the bottom is BABAB. So here, first of all, we have to connect its gates together, right? So we have to connect all the gates of it together. So you can see the gate of all of them. We need to connect them in series. And the bit gate also needs to be fully connected, right? You can see this. It's like tying shoelaces, crossing them over to connect. Now here, we need to pay attention. You can see that for B's connection, or A's connection, I will use what? The gate, right? You see, part of this cross connection is done using the gate for the connection. This is what we mentioned before, that the gate is the poly. Poly can be used as a connection in some cases. What is the situation? It can be used in this case. Why use poly? Because if we use poly, we can save a layer of metal, right? Look, what is this blue one? This blue one is M1. So after we use this poly connection, we can actually only use M1 to solve the problem of connecting the meter line. If I don't use Polo, then I must use M2, right? I must use M2 because I have already used M1 at this position. That is the connection of A, so I have to use M1 when crossing it. So if I connect B and try to cross it over, I can't use M1 anymore, right? Because that would short circuit M1. There definitely has to be another layer. If I still use metal, then I would have to use M2, right? In that case, I would be wasting a layer of metal here, actually. So, what can I do? I can skip using M1 and directly use what? I can directly use poly for the connection of B, and that would solve the problem, right? Using poly takes care of it. But what should be noted? The number of polos used in the connection between A and B must be the same, otherwise what will happen? The integrated resistance of the JIT of A and B is different, and there is a difference. So here you can see that the number of times the polity of A and B is used is the same. As for B, you can see how many times I used poly here. Here is once, right? Is it once here, right? What about B? I used 2 polys, so I used poly twice to connect. Now looking at AA, it has also been used twice, right? Yes, it has been used twice. The same goes for metal, right? The same goes for metal. So in this way, the integrated resistors of the gates for A and B are also consistent, right? They are also consistent. This is poly. And what's next? It's the source and drain, right? The source and drain are quite simple. The source refers to A. This is this. The circle is the position shared by A and B. We are all this circle. So pull out the position shared by A and B and finally connect them together, and it becomes a circle. So these non-common positions correspond to their respective lows, right? Then we connect this low out. So here I have to use M2, right? I need to use M2 because I have M1 below, so I need to connect the drain out using M2. Then, with the help of the pupil one, I can use M2 to connect it out, and that forms it. Positive and negative V out. And over here, what do we have? The positive and negative microsignals. So, in this way, we've completed the drawing of a common reference Hart's input transistors. So this is when we are drawing the input transistors of the operational amplifier. Using this reference Hart method to achieve a layout match. So it can suppress the higher order gradients in the XY directions, right? The changes in the parameters gradients ultimately make A and B, which are the 2 devices we processed, more consistent, right? More consistent.
All right, let's take a look at how to deal with the set action issue. Because of this problem, when we are drawing layouts, we often use the concept of a unit device. This concept of a unit device is also a very important piece of knowledge in our analog integrated circuit layout design. It's also a very important piece of common knowledge. Let's see how to use this unit device. For example, if we want to draw 3 transistors, 3 MOSFETs. Well, if we want the width to length ratio of these 3 MOSFETs to be in a relationship of 1.24, then we should draw its gate area right. For example, the blue area is our gate area, so we first draw the first transistor. Alas, we draw a MOSFET like this with a WBL, right? This is W to L. When we draw the second MOSFET gate, because its width ratio is twice that of the first one, we change its W to twice W, right? So when we draw it, it is twice the W to L. And for the third one, of course, it is 4 times the W to L, right? So we draw 3 transistors, and their width ratios are WBL2 times WBL and 4 times WBL. So we imagine that the width ratio of these 3 transistors should satisfy a relationship of 1 to 2 to 4, right? But the actual situation is not like this, because of the existence of set action, so their actual spaciousness ratio cannot meet the 1-to-4. Let's take a look. When there is set action, we can see that what we draw is actually a dotted box, right? Set action causes a fixed deviation. In the W direction, the deviation is delta W. For L, the gate drawn with W to L ratio becomes W, delta W, L, delta L after processing, forming the yellow part. Assuming this ratio equals A, for the second transistor, the 2W to L ratio forms part of the yellow area. Actually, it's the yellow part inside, right? So how big are the width and length of this yellow part? If we calculate it, it becomes W delta W over L delta L, right? Now let's assume we consider this ratio to be equal to 8. If it equals A, let's take a look at the second transistor. We have drawn a gate with a width to length ratio of 2W to L, and after considering the set action, it becomes part of the yellow area, right? And we need to note that the set action is fixed, right? So on the L side, there will still be an issue with a delta L set action. On the W side, there will also be a corresponding dirty W, which is equal to the one we just mentioned. The set action. So let's take a look at the second transistor. What is its actual width to length ratio? It's 2W delta W over L delta L, right? Now, let's examine this ratio. This ratio is obviously not equal to twice A, right? It's not equal to twice A. So you're saying that the second transistor is not actually twice as wide as the first transistor. And the same goes for the fourth one, right? The fourth one is 4 times W, which is dirt W divided by L minus delta L. He is obviously not equal to 4 times A. So in this case, after considering the side lessons, if we draw it according to WBL2 times WBR and 4 times WBL, it is difficult to guarantee these three transistors. They can reach a relationship of 1 to 2 to 4. So what about this thing? It is not advisable to draw them this way. We must use the unit device, which means using a single unit component. Then, we can control the ratio between them by paralleling these unit devices. So, in the same situation, we need to draw 3 transistors with a width to length ratio of 1.24, right? Let's take a look at the first transistor. For the first transistor, we draw it, and after considering the set action, its actual width to length ratio is A, right? It's actually A. Now, when we draw the second transistor, it's different from before, right? Previously, we simply doubled W. We drew a very large transistor, but because of the set action, its width to length ratio can't be guaranteed to be double, right? But now, using the unit device, it's a different story. So, how do we handle the second transistor? We place 2 gates with the same width to length ratio as the first transistor, and then we connect them in parallel. By doing this, we achieve the effect of a width to length ratio of 2W to L, right? Let's take a look at how this is specifically implemented. The width to length ratio of the first transistor is actually like this, right? Then, for the second transistor, we make 2 copies of the first one. So for each copy, you can see that each one, its spaciousness is W minus delta W. And then, it is L minus over L, subtracting delta L. Each part is like this, and then we connect the 2 in parallel. So after paralleling, the amplification factor is directly multiplied by 2 in the numerator, right? It's directly multiplied by 2. So we can see that the overall width to length ratio is 2W dirty W over L delta L. This result, when compared to the first one, shows that it is exactly double the first one. So, in the second case, its effective width to length ratio is 2A. Then by analogy, when we quadruple the ratio, we copy the first transistor into 4 parts, and then connect them in parallel. R4 actually carries it. It's multiplied at the very front of the numerator. This way, the overall width to length ratio becomes 4A. So, by using this unit device approach, we can achieve an accurate 1.24 ratio. The relationship of strength. So this is the unit device, which is very important for addressing this situation. So the same principle applies to transistors, resistors, and capacitors. That is, when we want to design a fixed proportional relationship, we must use a unit device and then connect them in parallel to achieve an accurate replication. And the exact proportion of the enlargement, rather than simply directly enlarging the length of a certain side, is impossible to achieve. Because if you directly enlarge the length, it will not be proportional to the citation, so it will lead to a scaling. Your final width to length ratio will have some deviation, so you definitely need to use what? The unit device, right? The unit device. Alright, next, let's take a look at how to deal with random mismatch, this kind of random adaptation. The main way to address this is actually through large size, right? Large size. So why does a larger size help suppress random mismatch? Let's look at an example. For instance, if we want to draw a square, the length of its side is x. The side length is x. So we consider the impact of random mismatch, right? When we process this pattern, various random phenomena during the manufacturing process can cause the edges to be quite irregular, right? Now, looking at it comprehensively, let's say there's a deviation in the height direction of this square, which we call delta y. Then, if there's a horizontal deviation, that's delta x. After these deviations, examine the actual area and its standard deviation. Now, calculate the rectangle's area after processing. X plus delta x, y plus delta y. Both sides have deviations. Delta x and delta y are random variables. Let's calculate the actual area of this rectangle after processing. The actual area must be x plus delta x, and then multiplied by y plus delta y, right? That is to say x, that is, there will be 1 on both the vertical and horizontal sides. Deviation, there will be a deviation. Of course, this delta x and delta y are random, they are random quantities. Then, what happens when I open it? Well, it is a formula like this, right? In this formula, if you notice, there is a delta x multiplied by delta y, so we think it is a high-order term, right? Because x and delta y are originally random deviations. This deviation itself is relatively small. So when you multiply the two, it definitely becomes even smaller. Therefore, we can ignore this term, right? Let's focus on the remaining part, okay? This part represents the area after processing, right? Now let's take a look at what the ideal area is. The ideal area is definitely x squared, right? It's x squared. Now let's take a look at the mismatch. The mismatch is defined as the actual area minus the ideal area, and then let's see what percentage this deviation represents of the ideal area, right? After we calculate it, we'll find that the x squared terms cancel out, right? Then, after canceling 1x from the numerator and denominator, the percentage of mismatch is this much. It is so big, so pay attention, because delta x and delta y are both random quantities, right? So the average value of delta x and delta y is 0, right? The average value is 0. So you see, on average, this mismatch is definitely relatively 0, but we must pay attention. Since they are random variables, what we care about is their standard deviation, right? It's their standard deviation. So we want to calculate the standard deviation. Let's look at delta x and delta y. If we consider the standard of both of them, it is sigma x, that is, the standard deviation of delta x, and delta y is sigma x. In this case, after we add the two random quantities, what is the standard deviation? It must be the square root of 2 times sigma x, right? And since x is a constant, we can factor it out, right? So, looking at it this way, the standard deviation of the mismatch is this much, right? It's the square root of 2 times sigma x divided by the larger x. So here we can see that delta x is a fixed value, right? This is definitely determined by the stability of the manufacturing process. If the process stability is poor, then it will be larger. If the process control is good, then it will be smaller. This is probably going to be a bit smaller, right? This is something that designers can't control. So, what can designers control? It's x, right? You can see that if x increases, the standard deviation of the adaptation of this area will become smaller. Right? If the area is smaller, the standard deviation will increase. So what does this mean? It means that if we draw a very large shape, like a big rectangle or a large square, for example, if I have a very large square, and then I draw a smaller square, the deviation of these two squares will definitely be such that the deviation of the larger square is smaller, right? The deviation of the smaller square will have a much larger standard deviation. So through this analysis, we can see that using larger dimensions can reduce the compatibility of the components, right? So, generally speaking, there's a model for this kind of random mismatch, and the model looks like this. AP is a certain parameter, a specific parameter, and it has this kind of... It's a fixed coefficient determined by the process, and you can think of it as a fixed coefficient dictated by the process. Then, when you take the square root of WBL, what is the square root of WBL? It's actually the linearity of this shape, right? The linearity of the shape, W multiplied by L, gives you its area, right? The square root of the area is like its side length. You know, if we consider it as a square, then that's its side length. Then what? After this division, the resulting parameter is the adapted standard deviation. The large AP is determined by the process, but WBL is determined by the designer. So if you multiply L by a large W, you can get a smaller adaptation of this parameter. 10 times. So this is why using a large area can achieve the same level of adaptation as a small one. Of course, this comes at a price, right? If you use a large area, what about me? The area of your layout is relatively large, so you occupy more area, right? Secondly, it will bring more parasitic capacitance or resistance, right? In this case, it will make, when the circuit is working, if you need to drive this device, it will require more power consumption, right? Let's take the simplest example. For instance, when we draw a capacitor, if we want to achieve a very good match between capacitors, then we have to make the capacitor very large, right? As I just said, if the area is large, we can make its sigma smaller. So what happens when the area is large? Then the capacitance will definitely be very large, right? The capacitance will be very large. For example, in order to achieve a good match, I may need a 4 WB capacitor. If I use a small capacitor, for example, a 0.4 pF. If it's 0.4 wholesale, then its adaptation will definitely be larger than that of the 4 pF, right? So if I use a 4 pF capacitor, I can achieve a good matching. But here's the problem. If I use a 4 pF capacitor for this circuit, just think about it. Driving a 4 pF capacitor will definitely require much more current than driving a 0.4 pF capacitor, right? In that case, the power consumption will increase. So this precision, right? In analog circuits, we talk about the precision of precision circuits. It's directly related to the public account, right? If your precision is high, then obviously your power consumption will also be high. The most direct reason is that if your precision is high, the size of your devices will be larger. And when you drive such large devices, your current will also need to increase. So it's clear that your power consumption will also increase. Right, using a larger size can reduce random adaptation. So, just now, we quantitatively analyzed how a larger area can lead to a smaller standard deviation of random mismatch. Now, let's take a qualitative look and intuitively understand why a larger area results in smaller deviations in these parameters. Let's take this transistor as an example. For instance, we have this transistor with a width to length ratio of W to L. Now we will decompose this gate into smaller parts. We break it down into several smaller transistors, each with a width to length ratio of W0 to L0, and connect them in series and parallel, right? So, along the channel direction, we handle this transistor in a series configuration. For the direction perpendicular to the channel, we will handle this transistor in a parallel configuration. In this way, a large WBL can be considered as several, right? It consists of n units, right? N units of the width to length ratio, combined through the series and parallel connections of small transistors. So in this case, let's take a look at a small transistor. Each transistor has its own parameters, right? It has its own threshold voltage, its mobility, its oxide capacitance per unit area, and so on. So each of these parameters is present in every transistor, right? But when combined, the total parameters of these transistors, after being connected in series and parallel, effectively create an averaging effect across the entire range, right? It's an averaging effect, including its width to length ratio, which is also an average result. This means that it will add up the W0 and L0, right? After the addition, it will result in this WBL. Now, during this addition process, in fact, the deviation, that is, the relative percentage of the deviation, is gradually decreasing, right? This means that as the number of components increases, as the number of decomposed components increases, so these parameters, their percentage of deviation is gradually decreasing, right? This is why a relatively larger area can lead to a smaller adaptation level. So what is the most intuitive application of this principle? For example, when we use this capacitor device, usually the foundry's process documentation will provide a picture like this. So what about this picture? Pay attention to the horizontal axis. What is it? It's 1 over the square root, right? So the horizontal axis is 1 over the square root of W times L. So that means the square root of the area, right? The square root of the area. In other words, it actually represents the limits of a geometric figure. For example, if I draw a square, then it's the length of the square's side, right? The side length is in the denominator, and then we take the reciprocal of the side length. This is its horizontal axis, so its unit is micrometers, 1 power, micrometers to the power of 1. Now let's take a look at the vertical axis. The vertical axis represents the percentage of capacitance compatibility relative to the average capacitance, and the standard deviation of this percentage, right? The smaller the standard deviation, the smaller the adaptation level, right? Let's take a look. This is basically a linear relationship. That is to say, as W multiplied by L increases, that's the direction, right? This direction is to increase WBL because the square root of W times L is in the denominator. So the larger the W times L, the smaller the entire term. That is, the closer to the origin of the coordinate, the larger the area of the device. So the larger the area, the smaller the deviation, the smaller it will be. So through this, we can see this. The relationship between fit and area. What is the use of this graph? It will guide the designer to choose the capacitor size to use as the device according to your matching requirements, right? For example, if I want to make a circuit with a 10-bit precision, such as a 10-bit ADC, what is the bottom line requirement? Then I must achieve this deviation 1% to it, right? That means 0.1% is here. So I look at it and hey, this 0.1, how much capacitance should I use? I can find it through this table, right? Well, the table shows it here. So this is 0.15, right? That means if my capacitor is a positive capacitor, then the reciprocal of its side length equals 0.15, right? So how much is X? That is the reciprocal of 0.15, right? So roughly, how much is it? About 7 microns. So if I take a square with a side length of 7 microns and use it as a capacitor device, then its matching accuracy can reach 1%. 1%. If I want to achieve even higher accuracy, you can see that the side length is gradually increasing, right? For example, if I want to reach about 0.06% accuracy, then I would need a capacitor of about 20 micrometers, right? If the side length of a square capacitor is 20 microns, then its area becomes larger, right? Obviously, its capacitance value also becomes larger, so it consumes more power, right? This is what we just emphasized. To achieve better matching, you use a larger device area. The trade-off here is that your power consumption will increase. So this is how we address the random mismatch issue.
All right, so what we've talked about so far is some of this, some mechanisms that can cause this device to adapt, right? Then we also introduce some layout methods to deal with these. A means to cause the phenomenon of layout adaptation. So the above means. Basically, we use the MOS transistor as an example to illustrate. Of course, the above means can actually be transferred to, on our flagship, for example, our capacitors and resistors. We can use the above methods to deal with our adaptation problems. Then we are working on a match between capacitors and resistors. Special instructions. Let's take a look at what we need to do if we want to match the capacitor devices. So what principles should we follow? Of course, the methods just introduced above can be used for capacitor matching. Let's take a closer look. For example, if we want to match capacitors C1 and C2, we can see that first. First, we need to implement a common centroid layout method. C1 and C2 are arranged alternately, forming a square cross layout. The purpose is to achieve common centroid matching. Next, consider the Dami period. The surrounding environment should be consistent. During this period, we need to surround it with matching devices. Note that these devices don't have to be identical to C1 and C2. We don't need identical small square capacitors. Just arrange it to be a public office. Then, what else should be done? We need to make a Dami period, right? We have emphasized before that the environment around the period should be the same. So in the Dami period, you can see that there are so many Rice devices around it, Rice devices. What about here? Well, it should be noted that these close-fitting components do not have to be exactly the same as the unit components C1 and C2. In other words, I don't have to surround it with the same small square capacitors. If you surround it like this, of course it is a high-density device, there is no problem. For example, if I draw squares around it, it is used as a dense tie line, this is no problem. But what is the problem? It will increase your layout area. Right, so usually I just need to draw a small line. There's no need to make it look exactly like C1 and C2. as long as the edges of C1 and C2 can see that the surrounding environment is completely the same, that's enough. For example, after I draw the dummy, you can see C2. As for C2, its top, bottom, left, right, and bevel angles all have this structure, right? This is the structure. Now let's look at the edge C2. After we take rice into consideration, the edge environment of C2 is the same as the CR in the center. So in this way, it has already played the role of a unit, and the utilization rate of this area can be increased. This is something to pay attention to. Another thing to note is the details of the dummy. Some people might draw it like this, connecting everything and making the corners look like this kind of shape. It might seem like they are wrapped with dummy, but be careful. In reality, the shape at the corners is different from the inside. You can see that the corners inside are not connected. They are empty, and they are not connected. The dummy at the edges, should not be connected either. In this case, the dummy at the edges should be a very small segment, not a rectangle. Note that this is for dummy devices. Also, after using dummy devices, these dummy components must be electrically connected. The matching devices cannot be floating. For example, if I have these capacitors placed here, I should not leave the capacitors above and below unconnected. The edge of the dummy should not be connected, so in this case the dummy at the edge is a very small block, not a rectangle. Note that this is the flagship of rice. Then we must also pay attention to the fact that after we use the flagship of rice, these rice devices must be electrically connected to it, that is, the close-fitting devices cannot be floating. For example, these are all capacitors. After I put these capacitors here, I will not connect these capacitors above and below a few hundred. Leaving them floating here is not acceptable. They must be connected. Moreover, since they don't serve any functional purpose in the circuit, these devices must be shorted out. They definitely need to be shorted. So it's important to note that matching devices must be shorted out. For example, for capacitors, I need to connect the top and bottom plates together. And it's best to connect the top and bottom plates and then connect them to ground. So in this case, you must also include this component in the schematic. In the schematic, you need to show the top and bottom plates of these capacitors. After connecting, you need to connect it to the ground. This is a representation of the dummy devices in the schematic. So if you don't put one like this on the schematic. As for the device, I added a lot of rice on the layout. Then, the rice is indeed short-circuited up and down, and then grounded. So when you do LVS, if you don't do any optional operations, then it will report an error, because it does detect a lot of short-circuited devices on the layout, right? But there are none on the schematic, so it will report an error. Then there is usually an option in the LBS, that is, in the specific settings, to ignore such short-circuited devices. What happens after ignoring the short-circuit device? It will not check these rice devices. In this case, it can still pass. Or you can add such a device to the schematic diagram. I personally recommend adding such a device to the schematic diagram, because after all, if you ignore the short-circuit device, if you do short-circuit a useful device, it means that it is not short-circuited originally, but you accidentally drew it as short-circuited when drawing the layout. In this case, the flagship will be ignored, which will increase the complexity of your troubleshooting. So you might as well put these components step by step on the schematic diagram, according to the connection relationship of the actual schematic diagram. So we need to conduct a complete LVS check, right? So this is during the dummy period. Now, speaking of which, earlier when we were discussing transistors, there was a point we need to review this again. Let's go back to the issue of matching with transistors we just discussed. Here, I want to emphasize one more thing about this transistor, which is... oh no, it's this. This means that the transistor must be short-circuited, right? It must be short-circuited. Just now we talked about the capacitor being short-circuited. So for the transistor, it is also short-circuited. But what else should we pay attention to? We must remember their parasitic contribution. That is, their parasitics. The problem of parasitism. In addition to short-circuiting them, we also need to consider their parasitic problems. For example, the connection of this transistor, you can see from the schematic diagram that this device has already achieved short-circuit treatment, right? For example, this circle, we've connected its drain and source together, right? We've connected them all together. So it is obvious that this is a short-circuit device. So this device must be non-functional, right? It is definitely non-functional, but be careful. It's this round end, right? What is it at the end? It is connected to the circle of the useful device. This is a line that connects everything, right? They are all connected. Why? Because we use the finger drawing method. So if you look at this dummy device, it has a circle that is shared with the circle of the normal device, right?
You see, this round end is shared with the round end of the normal device, and the same goes for this side because we use the finger method for sharing. So, since the round ends are shared, this round end is actually connected to the round end of the useful device, right? So what's the problem with this? It will increase parasitism, right? Even though the dummy device has been shorted, its parasitic capacitance to ground at the source cannot be ignored. This is something that cannot be ignored. Although the parasitics between the source and drain have been eliminated, because the source and drain are shorted, the parasitic PN junction between the source and substrate still exists, especially if you have a lot of dummy devices. The parasitic capacitance at the source can still be quite significant. So, this can lead to an increase in the parasitics at the source, and this is something we need to consider. After you draw the dummy devices, you really need to consider the parasitics, right? There are still parasitics to think about. So how can we avoid these parasitics? Actually, a better approach is to not use the finger method, but instead use the multiplier method. Use the M method. The M method means that each tube is an independent tube, so the rice is also independent. In this case, I can ground the rice circle, right? Grounding. In this way, I will not have any electrical connection with the normal device. So it is completely independent. In this case, it only plays a role in the processing and protection of the layout, and will not have any impact on the electrical characteristics. This is what we must pay attention to when we draw the density. Yes, of course, it is not said, and it does not mean that it must be done this way, if you are talking about my S end. If I'm not sensitive to its parasitics, right, then the size of the parasitics doesn't really affect the characteristics of my circuit much. In that case, you can connect this round end to this one using the finger method. That's fine. However, if you're sensitive to parasitics and can't have large parasitics at the source end, then you need to consider whether to break this unit apart, right? So what does it mean to break it apart? It's similar to this, right? You can see that this capacitor has already been separated, right? Now, I can ground these surrounding capacitors, and they won't have any electrical connection with the capacitors inside. So this is the dummy device, right? You can see that here we've actually used two techniques. One is the matching of the supply capacitance, and the other is the dummy issue, right? These are all consistent with what we discussed earlier. And what else do we need to use? We need to use unit capacitance, right? Unit capacitors are definitely necessary. If you want to match, you definitely need to break down C1 and C2 into several equal units and then connect them in parallel, right? So this is the concept of a unit capacitor. And then this is the common gate, right? Common gate, this is the dummy device, and this is all the same as what we just discussed. So what's slightly different from matching our capacitor devices? There are two things to pay attention to. The first one is shading. Shielding. Shielding is about protection, or you could say it's about shielding. So you can see that we've drawn a circle around this capacitor, right? We can think of it as a substrate contact. It's a circle of substrate contact. The substrate ends here, and then we connect it to ground to use it as a protection. What is this? This is a gathering, a gut ring. We will introduce it in detail in the 5th lecture. Gathering is a specific one. How to use it? Well, we can first take a look here. Let's draw a circle around this capacitor. This way we can shield the substrate underneath the capacitor. The purpose of this is to reduce the noise of the capacitor. Reduce the noise of the capacitor. Then what? The characteristics of the capacitor will be better, so it needs to be shielded. Then, there is another thing that needs to be paid attention to. Connection contribution. That is, the connection of the capacitor, what will it cause? Parasitic capacitance, right? Because the capacitor device we drew, after we add the connection, this connection will contribute new capacitance. If the parasitics of the connection line of the different capacitors are different, then it will cause deviations between C and C2, right? For example, if I have a lot of CE connection wires and very few C2, then it is very likely that C1 will be too large, which will make the value of C and C2 larger and larger, and then it will be larger and higher than normal. So in order to avoid this problem, we must make the length of the line connecting C1 and C2 the same. So if you can see this line, it is also the same. The process of symmetry treatment means that each capacitor's connection point is the same, right? They are all the same. So this is about the impact of the connections, right? The influence of the connections. So what else should we pay attention to? The placement of the capacitor. what should we pay attention to? Away from power devices and away from this stress area. So actually, power devices can cause stress issues because power devices generate heat, right? When the power is high, they produce a lot of heat, and once they heat up, it creates a temperature gradient distribution. So with different temperature gradients, it can cause some stress issues in the body. Once stress occurs, it will affect our capacitors, which in turn impacts our matching characteristics. For example, let's say this central position here is where we have a power device. We placed a high power device here, and it will generate heat, right? It will generate heat. This will create a temperature gradient, right? A temperature gradient that radiates outward from the power device. So the temperature at the center will be the highest, while the temperature at the edges will gradually decrease. There is such a thermal gradient. If we have two capacitors, C and C2, we want to match C and C2. Then, let's look at their placement. C1 is far away from this. The power device C2 is relatively close to the power device. So this kind of placement is really not advisable. It will lead to serious deviations in the characteristics of C1 and C2. Why? Because C1 and C2 experience different temperatures, right? The area where C2 is located has a higher temperature. The temperature of C2 is higher, right? So the temperature where C1 is located is lower. So in this case, this will cause some deviations between C1 and C2. So placing the two capacitors this way is not advisable. So what is a better approach? The better approach is to place C1 and C2 in parallel so that they are in the same position in the temperature gradient. This way, C1 and C2 will have the same temperature influence. That means the temperature affects them in the same way. However, we also need to be very careful with this approach. Why do I say that? Because when we place them, it's really hard to determine what the direction of the temperature gradient actually is, right? So what if you think the direction is the temperature gradient direction, but what if the temperature gradient is actually in this direction, right? Or is it an inclined direction? It's really hard to control and say that C1 and C2 are at the same position with the same temperature. So what's the best approach? The best approach is to keep a distance, right? Away from the power devices. I may not know exactly what the temperature gradient looks like, but if I place it further away from the power device, that should be fine, right? Just keep it away from the power devices. What if we stay away from power devices? No matter how I place C1 and C2, whether horizontally or vertically, or however I arrange them, I won't be affected by this gradient, right? Because at this position, there is no temperature gradient. The temperature is the same everywhere. So this is the best approach. Now, how far should this distance be to be appropriate? Generally, it's about several tens of micrometers. Generally, it is tens of microns. This distance can reduce the influence of temperature and stress. Of course, this also depends on the size of your power, right? If your power device is, if the power is very high, then you may need to increase the distance appropriately. So this is a problem that we need to pay attention to when placing capacitor devices. So let me summarize the principles we should follow when matching capacitors, right? There are several principles. Let's look at them one by one. The first one is that they must have the same geometric dimensions. In other words, the two capacitors must have the same appearance to match. For example, if I have one capacitor that is square, and then I switch the other capacitor to a rectangular shape, trying to match these two would be very difficult, right? They must have the same geometric shape. The second principle is to use larger unit capacitance. Larger unit capacitance requires dividing the device into units, like capacitors, for matching. It reduces edge effects but raises power consumption. The third principle is a common centroid layout, and the fourth is using surrounding devices. Then we need to use a larger unit capacitor. A larger unit capacitor. So a larger unit capacitor, first of all, it can reduce the edge effect. Then what is the more important thing? The more important thing is that when the area is larger, its adaptability will be reduced, right? But it has negative effects. What are its negative effects? Its power consumption will also increase, so this should be paid attention to. The third one is to use the common finger center arrangement. You have to use the common finger center. In this way, you can deal with the gradient problem, right? And the fourth one is to use devices. Use devices to surround so that the environment around the capacitor is the same. Next, we need to have protection and shielding, right? This is to shield against noise. We also need to consider the parasitic issues of interconnects. Parasitic effects from interconnects can affect capacitance values, which can lead to problems with capacitor matching. Then it is also important not to place any interconnection lines on top of the capacitor. This is actually similar to the metal over transistor we talked about earlier. That is, you'd better not place this on top of the capacitor. Don't place any routing lines above them. Well, finally, the capacitor should be placed in a low stress area and away from power devices so that the fatigue of the capacitor will be better. So the above are the matching principles that we should pay attention to when drawing capacitor devices. Now let's take a look at resistor devices. We won't explain resistor devices one by one. Its basic principles are similar to those of the mode devices and capacitor devices we mentioned earlier. So let's summarize it. When we draw capacitors, we need to follow certain principles to match them. First of all, we need to use the same material. This is different from what we just discussed regarding active devices and capacitors, right? We didn't mention the need for the same materials earlier. However, for resistors, we do mention the importance of using the same materials. Why is that? Because, as we mentioned before, when implementing resistor devices in integrated circuits, we can use many different types of resistors, right? For example, there are polysilicon resistors. What else is there? There's also the injection, right? The N-type or P-type doping injection, and this kind of injected capacitance. What else? The N-well, right? The N-well can also serve as the substrate. So, we have the injected resistors and N-type resistors, etc. As you can see, there are quite a few types of resistors. Now, if we want to do matching, we must use the same materials, right? For example, if I have resistor A and resistor B, and resistor A is a polysilicon resistor, if resistor B is an N-well resistor, matching A and B is impossible due to different materials. Use the same materials, like polysilicon or N-well resistors, for both A and B to achieve matching. Different materials make matching unachievable. Use the same materials to match resistors. Ensure they have the same geometric dimensions and orientation. Place them very close together. Then you can do matching, right? Or if I use N-well resistors for both A and B, you can also do matching. But if you use different materials, it is impossible to achieve. This is the first very important point. That is, if you want to match resistors, you must use the same material. The second thing is that they must have the same geometric dimensions and the same placement direction. We have talked about this before, right? The same applies to resistors. Then you also need to pay attention to placing them very close. If they are placed very close, actually, this is applicable to both capacitors and MOS transistors. The devices you match must be very close. If you match, for example, this is my chip, I put the A7 key here, and I put the B key diagonally here, I want to match A and B. This is also very difficult because the distance between them is very far. The deviation of the parameters in the area will be relatively large, so they must be very close. If I want AB to match, then I put AB here. So, if I place both A and B here, making them in an I shape, then I can perform a matching operation. The next point is to arrange the capacitors in a forked layout. The reason I didn't mention the supply line here is that generally, resistors are long and narrow, and we often draw them in a serpentine structure. So, it's more suitable to use this forked structure for axial matching. You also need to pay attention to using large devices, right? These large devices must be utilized. Now, the next point is about stress issues. They should be placed in a low stress environment and away from power devices, which is similar to what we discussed about capacitors earlier. Finally, protection and shielding are also needed. Shielding means that the noise is smaller. And if the noise is smaller, it is also conducive to matching, right? Because if two devices experience different noises, their characteristics will definitely deviate. So this is the principle of capacitor and resistor matching. Then let's take a look at an example of resistor matching. For example, here we have R1 and R2. When we want to do something with R1 and R2, this is a core matching operation, right? This is a core matching operation where R1 and R2 alternate like R1, R2, R1, R2, and so on. All the R1s are connected in a serpentine manner, right? And R2 is also connected in a serpentine manner. Additionally, we need to make sure that the devices on both sides are large enough, right? This is a typical example of capacitor matching. Drawing methods, right? Drawing methods. All right, so based on what we've discussed, we're talking about these devices, right? Whether it's active devices or passive devices like capacitors and resistors, the focus is on how to achieve matching for these components. Next, let's introduce the matching of interconnect lines. In addition to matching the components, the interconnect lines also need to be matched. So, what should we pay attention to when matching interconnect lines? Let's focus on a few key points. First of all, when it comes to interconnect line matching, the most important thing to pay attention to is its parasitics, specifically the parasitic capacitance and resistance, with a greater focus on the parasitic resistance. When matching interconnect lines, you need to pay attention to the resistance of your wires, whether they are metal lines, deposited lines, contacts, or vias. You should be clear about the resistance characteristics of these materials that serve as interconnections. You need to minimize the impedance of your interconnects, bring it down as low as possible. Of course, this impedance isn't just R, right? There's also C, so you need to minimize both R and C. Then what else should we pay attention to? We should pay attention to the fact that for the differential path, you should have the same impedance. If it is a differential path, the parasitic environment of your differential line must be the same. In this way, you can make your differential signal more matched. Let's take an example. For example, this one. Arrangement. If these two tubes are A and B, what are these two transistors? Differential, yes, a differential pair. Then, if we want to send a power supply to this differential pair, provide a power source, for example, or apply a certain voltage. The wire comes from the left, connects to A, then B. This connection causes issues. It won't match. Device A's path is short, so its resistance is small. To reach B, it travels a longer distance. Thus, A's resistance R is small, but B's parasitic resistance R is large. If current flows, A's IR drop differs. So, during the journey to B, it has to travel a long distance before reaching B. This way, the integrated resistance R of the connection to A is relatively small, right? But for B, its parasitic resistance R is relatively large. It is relatively large. In this case, if a current flows through this line, then it is obvious that A will suffer an IR jump. What should we do? We should make it smaller, right? It should be smaller. And the IR drop suffered by device B is also smaller. So what happens? The voltages obtained by these two devices, it's different now. The voltage that device A receives is higher, right? The voltage it gets is higher, while the voltage that device B receives is lower, because the IR drops are different. So in this case, the two devices, because of the mismatch in the wires, it will cause this. The voltages are different, and this will lead to an offset, right? So, how do we draw it? It has to be done this way. According to the drawing method below, you need to connect the line. Connect it from the left. First, connect it to the center position of the two devices, and then separate them, right? What is this? It's a drawing method similar to a binary tree, this kind of binary tree representation. In this case, whether it is A or B, the path length it traverses is the same, so they have the same IR drop. Right, they both have the same, so the voltages they receive will also be the same. This way they match better. So, this is an important issue to pay attention to regarding wire matching. Alright, now let's take the folded cascode operational amplifier as an example to explain how to lay out and draw a schematic. First, let's take a look at the schematic of the folded cascode operational amplifier, right? So first of all, this part here is its input, the input differential pair. This part is very important. The input differential pair is crucial because it directly affects some characteristics of the differential pair. Below it is the pseudocurrent source for the input differential pair, right? Now looking to the right, we see the load section. The upper part consists of PMOS transistors forming a current source, while the lower part is made up of NMOS transistors, which create the cascode current source. So when these two current sources are connected in parallel, they serve as this. This is the load capacitor for the operational amplifier, as the output impedance provider for this operational amplifier, right? Now, let's take a look at this current source part, this part here. The PMOS here, this part, is this is a current mirror structure, right? This is a current mirror structure, and below it is a common source transistor. Then underneath we have the NMOS current source along with an NMOS transistor as well. So what about the layout? Actually, the deviation of the Costco components, these four components, actually has a relatively small impact on our op-amp. So what is important? The important thing is the input pair, and the upper and lower ones. The current source transistors, their deviations can have a significant impact on our operational amplifier. What we just discussed is the main part of the operational amplifier. Besides this main part, what else is there? It's the biasing of the operational amplifier, right? The biasing circuit is responsible for providing the current mirror, whether it's for mirroring the current or supplying the bias voltage. Now let's take a look at how we can lay out and draw the schematic for such an operational amplifier. First of all, we put all the components here, right? We just talked about this. This is the input pair. Then we separate the positive and negative paths, one with the blue one and the other with the light pink one, to distinguish them. Then our goal is to match the blue one with the light pink one, right? To match them. If the characteristics of the transistors can be made completely identical after processing, then clearly the matching degree of this operational amplifier will be quite good. In the end, its failure voltage will be very low, and its power supply rejection ratio will be very high. Well, how do we do it? Let's take a look. First of all, we put all the devices here, right? This is the input tube, and then this is the P-type current mirror, and this is the P-type, right? This is the N-type device, and then we put the N-type current mirror here. And this is the N-type pseudo-current source, of course. It is also a current mirror. Right. Then, let's first do this. We need to arrange all the devices in a square cross pattern. That means we have to make one common centroid, right? All the devices need to be arranged in a common centroid layout, right? So let's first take a look at this part of the P-type current mirror. We will start by arranging it in a such a way. ABAB, then what? BABA is a layout for the finger center, right? After the arrangement, what? Then we add the bias circuit to the middle. In this way, first, these two devices are arranged symmetrically around the bias circuit as the axis, creating a coaxial symmetric structure. Then, each part is arranged in a cross pattern for the common centroid layout. So this part completes a layout. Next, let's take a look at the bottom part. It's the same down here, which is the current mirror section. For the electrical path section, we need to create a common centroid layout. Then besides that, for the remaining parts, like this one, we also need to create a common centroid. And of course, the input differential pair needs to have a common centroid as well, right? Then we place the bias circuit in the middle. In this case, we have actually achieved what is called the symmetry at the transistor level, called symmetry at transistor, which is a matching at the transistor level. In other words, each part has been arranged in a common centroid. Our P-type electrical path has a common centroid, the control point for the P-type current mirror, the common centroid for the N-type current mirror, and the control point for the input differential pair. Then, the N-type electrical path also has its control point. So, after we arrange everything like this, what do we get? What we get is a result that has very good matching characteristics, right? We have all done the common centroid. Moreover, the corresponding parasitic lines definitely need to be arranged properly, right? So, in this way, we achieve very good matching characteristics. But what's the problem? The problem is that it has pull parasitics. We emphasized this earlier, that after you create the common centroid, your wiring definitely becomes more complex. And that complex wiring will lead to more parasitic issues. So its parasitic characteristics are relatively poor. So this is the advantage and disadvantage of this kind of layout.
Okay, let's look at the next layout method. What is the next layout method? It's called symmetry at top level, which means top level matching. How do I do it? Let's look at it. Well, actually, it is to place the whole device according to the schematic diagram. It is arranged symmetrically. I put all the blue devices on the left, and then the pink devices on the right, and then put the bias circuit in the middle. In this way, the whole layout is based on the bias as the central axis. Well, it forms a left-right symmetrical structure. In this case, The bias is placed in the center, and the positive and negative blocks are symmetrically centered. So this is a top-level question, a top-level symmetrical structure. If you draw the layout in this way, it will look like this. All the devices on the left are placed on the left, and the devices on the right are placed on the right, and then the bias is placed in the middle. In this way, the two devices on the left and right do not achieve anything. It is a cross-matching treatment method. So, its connection will be relatively simple, right? The connection will be much simpler. So, there's no cross-matching, right? This means that the same devices are all on the same side, making it easy to handle them in parallel. But what's the problem? It doesn't do any cross-matching, right? So, it doesn't suppress variations in gradient parameters. That's why we call this structure a tail differential structure. Now, when we mention the tail differential structure, it actually means that it's not a true differential structure. It's not really differential, but it does have its advantages. What are those advantages? Well, the advantage is that the wiring is very simple, so the parasitics are relatively better. The parasitics are very low, So, when we mention the tail differential structure, it means that it's not really a true differential structure. It's not genuinely differential, but it does have its benefits. What are those benefits? Well, the advantage is that the wiring is very simple, so the parasitics are relatively better. The parasitism is very low, The parasitic effect on the circuit is relatively small, but what about it? The gradient matching is relatively poor, right? Because there is no control heart. So, this is a top-level layout method, and it has its issues. Now let's compare these two layout methods and see in what situations we would use transistor-level matching, and in what situations we would use top-level matching. So this is actually related to the process node. Let's take a look at the evolution from wide lines to fine lines, like the transition from 0.18 microns. You can see that 0.18 microns serves as a boundary, generally speaking, for process feature sizes above 0.18 microns. What do we generally prefer to use? Transistor level matching. So, generally speaking, for these coarser feature sizes, we use transistor level matching because the parasitic issues are relatively small at these process feature sizes. So, if the parasitic problem is relatively small, I can use more complex wiring, right? More complex wiring, but as the process feature level is reduced to deep submicron or tens of nanometers, the parasitic problem is relatively large. The parasitic problem is quite serious because the distance of all metal wires will be shortened. That is, the thickness will be reduced. In this case, the parasitic problem will be aggravated. If the parasitic problem is aggravated, then if I use more complex transistor body matching, clearly this will lead to more serious parasitic issues. So, at these smaller sizes, we usually prefer to use what's called top-level matching, where I create a symmetrical structure with a central axis at the top level, and that works just fine. On the left and right, I won't do the matching for the supply core. Now, around the 0.18 micron process node, we generally have a mixed situation. The so-called mixed situation means that not all transistors are matched using transistor-level matching, nor are all transistors matched using top-level matching. Instead, I will use both methods. So, how do we do this specifically? We focus on the critical transistors. For this kind of consensus matching, we might just use top-level matching for the less critical components. Right, so for example, in the analog process that we commonly use, for example, 0.1 micron or 0.3 micron, or for 90 nanometers, in this case, we might use a mixed approach. So, where are the critical areas? For example, the input differential pair, right? The input differential pair, along with our p-type current mirror and n-type current mirror. For these three, we might use the common centroid method, or to simplify, we might only use the common centroid for the input differential pair, right? The input differential pair is more critical. We use the common centroid for the input differential pair, and for the rest, we might just use top-level matching. This way, we can achieve a good balance. It's about using a combination. You achieve the best compromise between matching and parasitics, the best compromise you know. How do we choose this matching strategy? Alright, so in conclusion, let's summarize some basic principles we need to follow regarding the matching of analog integrated circuits. These are fundamental principles. There are several points. Let's take a look at them. First of all,
The first one is that the matching components must be placed very close to each other. We just talked about this, right? If you want to match two components, they must be placed very close to each other, not too far away. Second, the placement direction of the components must be the same. Then more specifically, the direction of the current flow should be consistent. The third thing is how do you use your device? The unit device is connected in parallel or in series. So, the unit device is an important concept. This is knowledge when we are laying out analog circuit designs. You must use a unit device. Also, you need to surround your devices with rice. The purpose of the rice is to make the environment around these devices uniform. This way, when they are processed, they will be consistent. So, it's essential to match the devices. Now, when matching devices, what must you do? Short circuit handling, right? As mentioned, it's crucial to ensure that the matching devices are short circuited. After short circuiting, you also need to pay attention to the parasitic issues, right? Even though the matching devices are short-circuited, they might still contribute some parasitics. So you need to consider the parasitics of your dummy devices. Short-circuit treatment, right? We just said that it must be used when matching components. So what happens after the short circuit? You still need to pay attention to its parasitics, right? Although the close-coupled components are short-circuited, it is possible that they will contribute some parasitics. So you have to consider the parasitics of your dummy. Then the next step is to say that the coaxial center and the co-fingering center match, right? This is the coaxial center and the co-fingering center match. What are these two for? The gradient change of some gradient parameters. In addition to matching the devices, what else do we need to do? We also need to match the wires, the interconnects. So you have to consider the parasitic issues of your interconnects. Whether it's metal pads, contacts, or wires, you need to carefully consider their parasitic resistance, right? Additionally, for interconnects, you also need to take their parasitic capacitance into account. So what must be allowed? The parasitics of the differential lines must be symmetrical. That is, the differential lines must be identical. Then the next thing is that everything must be symmetrical. Everything must be symmetrical. How do we explain it? This thing of ours, especially for this kind of differential structure. A differential structure must be symmetrical, left-right symmetrical. The layout should also be symmetrical from left to right. Device parameters, their sizes, must be large. This can increase power consumption, resulting in higher power use. When designing a layout for device matching, consider all these factors. The parameters of the devices, their sizes, must be very large. Only when they are sufficiently large can the matching be effective. However, this brings up a problem, which is that it can lead to increased power consumption, right? So, in summary, when we are designing a layout for matching a device, one of the most important things is to ensure that the area is large enough to achieve the required matching level. The increase in power consumption, right? It will lead to an increase in power consumption. So, in summary, if we want to draw a matching layout for a device, one of the most important things is that when I'm designing, I must ensure that the area is sufficient to achieve the required matching level, so it needs to be large enough. Well, under such conditions, when we draw the layout, we should consider these issues so that we can achieve the best characteristics of our circuit. If the area of my device does not meet my requirements, it does not meet our matching requirements, for example, my matching degree. This is the curve of the capacitor we talked about earlier, right? For example, what should I achieve in this matching? 1% matching? Then I can see from the table that I must have a 7 micron capacitor and I can achieve 1% matching, right? So if you have a 7 micron capacitor, then you can consider these. After following these principles, if your layout is processed correctly, it might achieve a matching level of 1%, right? But if I don't draw the capacitor at a width of 7 micrometers and instead draw it at just 2 micrometers, right? I only spent 2 months drawing. In this case, even if you consider all the above problems and use all these drawing methods on your layout, it is still difficult to achieve a 1% match, right? Because the device is naturally what is called random mismatch is very high, so it is difficult to achieve such a 1% match. So the first point is that we must meet the area requirements. Then, when we draw the layout, we need to carefully consider the matching techniques. Only then can we ensure that the processed devices achieve the expected level of matching. That's the situation. Let's look at this example. This is a fully differential comparator. As mentioned, everything must be symmetrical. It's a fully differential structure. This layout has a central axis. For example, there is a central axis here. It folds along that axis. After folding, they overlap. This gives a symmetrical structure, meaning both sides are identical. This benefits our circuit by suppressing common mode noise
It has a central axis here. For example, there is a central axis here, and we take this as the central axis. With this as the central axis, I can fold this layout in half. When you fold it left and right, they almost overlap perfectly. This creates a very good symmetrical structure, meaning the layouts on both sides are identical. This is beneficial because in our differential circuit, it effectively suppresses common mode noise. It will effectively suppress common mode noise or interference, as well as improve matching. So what do we mean by common mode matching? It means that the conditions on the left and right sides are the same. In other words, if there's a deviation on the left, there should be a corresponding deviation on the right. This way, using a differential structure, I can cancel it out. Therefore, it's crucial to ensure that the structures on both sides are identical, meaning that even if there are deviations, they should be the same. In this way, it will make the characteristics of our circuit better. Alright, that's all for this lecture.